Okay, moving on to Unit 4, Lesson 11 on both of the lines. So just like Lesson 10, I don't have the notes for you guys because I don't have any papers. So just go ahead and just watch the video. Actually, engage by thinking about it, or you guys can write it down your own notes. If you just sit there and watch but not processing it, you're not learning anything. So it's on you to be engaging with this video and actually processing, and pause if you need to think about something. Okay, so that's how you guys can learn. If you don't do it, I can't help you because you choose not to do it. Alright, so for this lesson, I'm going to use lines to think about situations. I want to show you guys the learning goals right here. We're going to create a graph that represents two linear relationships in context. So that means there's a background story for it. And we're able to explain the graph. We're able to interpret the graph based on the context, the story of it. I can use graphs to find an ordered pair that two real-world situations have in common. So we already learned how to write an equation for a straight line, or we know that an equation, we can use a line to represent it. And then so from the last lesson, Lesson 10, you guys were able to finish your exit ticket about the dime and the quarters. So just like this one, we have two lines right here representing the same situation. And then the point where they meet with each other, this will be your solution for a system of equation. Because I talk about we're going to start looking at two equations at the same time, and to find the answer is where they're going to meet with each other. Okay, so we're going to look more examples for that. Let's go ahead and look at the first part right here. What do you notice? What do you wonder? Go ahead and pause, take a look at it, and think about it before you start play again. Okay, you should have a couple answers in your mind, a couple questions. So let's see whether you guys cover these as well. The ladybug is moving from left to right, and the ant is moving from right to left. Okay, so they're going from the opposite side. The ladybug and the ants are each moving at a constant speed. So that means each second we are going the same speed. The ladybug is moving 8 units every 2 seconds, and the ant is moving 16 units every 2 seconds. In the picture at 6 seconds, the ant is no longer visible. At some point in between the 2-second picture and the 4-second picture, they pass each other. They're able to cross and pass through each other between the 2 and 4 seconds. Okay, questions. Where did the ants go in the last picture? At what time did they pass? At what tick mark did they pass each other? Did they wave as they pass each other? So these are questions that you might be wondering. So it's the same idea where there's two things going on right here with the same situation, but when I figure it out, when do they meet with each other? A different ant and ladybug are a certain distance apart, and they start walking towards each other. The graph shows the ladybug's distance from its starting point over time, and the labeled point 2.5 and 10, which is right here, indicates when the ants and the ladybug pass each other. I'm going to zoom out a little bit so we can see the whole thing. Alright, so now we see our graph right here. We have time on our x-axis. We have distance for our y-axis. Your x-axis is always your independent value. So your time keeps going on no matter what the distance is. So the time does not change based on the distance, but your distance change based on your time. So that's what we call independent and dependent. The ant is walking 2 centimeters per second. Write an equation representing the relationship between the ant's distance from the ladybug's starting point and the amount of time that has passed. This line right here is showing the ladybug speed. So for 1 second, the ladybug is 4 centimeters away. So that will be the speed for the ladybug. And then the ants, they just told us is 2 meters per second. Alright, before I write an equation, I want to make sense of it. So I just drew a line right here. I have the ladybug, I have the ant. I know that ladybug after 10 centimeters, which is right here, this is where they meet with each other. and it took the ladybug 2.5 seconds to get to 10 centimeters right here, but the ant is on the other side, and I need to figure it out for 2.5 seconds. That's the time that they share, but the ant will not have the same distance as the ladybug. So I need to figure out for the ant for 2.5 seconds where will he be at. So I take 2.5 seconds times 2 because that's the speed. That gives me 5. So that means in 2.5 seconds, the ant walk 5 centimeters. So right here for ladybug is 10. I'm going to use a different color. For the ants, it's actually 5. 1, 2, 3, 4, 5. So for the ladybug, for the ants, that is 5 centimeters. So that means the distance from the ladybug to the ant is 10 plus 5. 10 centimeters plus 5 centimeters. So that's the distance from the ladybug to the ant. So the total thing is 15. Okay, I'm going to start using these like background to write my equation. My distance will be d equals -2. -2 is the speed for the ant. Why is it negative? Because it's going the other way instead of going to the other way. So it's like going backwards from the ladybug. So -2t plus 15. All right, if you haven't already, draw the graph of your equation on the same coordinate plane. So I'm going to go ahead and plot this line that we have into this graph right here. To graph the equation, so let's just refresh how to do it. Starting with my y-intercept, which is 15, so I plot the point at 15. My slope is -2, so that means down 2 over 1. Make sure you look at your scale. Down 2 over, this is not 1. This will be your 1. So make sure you look at your axis right here. This 2 boxes is 1 for your x-axis. So I'm going to keep going. Down 2 over 1. Down 2 over 1. And then again down 2 over 1. And then I have one line right here. I'm going to go ahead and connect all the points. And then this is where they meet right here. So you can see that at 2.5 seconds, they meet at 10 centimeters for the ladybug. So this is your solution right here, the meeting point. All right, 10.3, Elena and Jada were racing 100 meters on their bikes. Both racers started at the same time and they're going at the same speed, constant speed. Here's a table that gives information about Jada's bike race. So this is about Jada. So the table is all about information for Jada. Number 1, graph the relationship between distance and time for Jada's bike race. Make sure to label and scale the axis appropriately. Okay. All right, so for math, your x-axis is always your independent. So comparing time and distance, time is always your independent. So I'm going to go ahead and write time on the bottom.
Please excuse this interruption.
Okay, I have my graph right here. My x-axis is the time in seconds. So I have 1. Each boxes would be like representing 1 second. My y-axis right here, I have my distance representing meters. I'm going up by 6 right here. 6, 12, 18, 24. So I'm going to go ahead and plot these 2 points. 6 seconds is at 36 meters. So 6 seconds, 36. 9 seconds at 54. Okay, so with the 2 point, I'm going to go ahead and plot another point. Usually it takes about 3 points to plot a straight line. So now I have one straight line right here representing Jada. All right, let's go to the next page. Elena traveled the entire race at a steady 6 meters per second. On the same set of the graph, we're going to graph for Elena. So I'm going to go back to the graph right here, and I'm going to plot for Elena. I forgot about the speed. Let's see. It is 6 meters per second. Okay. All right, since Elena is 6 meters per second, I'm going to go ahead and plot those points. For 1 second, it will be at 6. So that means 2 seconds will be 12. And then 3 seconds, 18. 4 is 24. 5 is 30. What do you notice right here? That basically Jada and Elena, they do have the same line. Okay, so realize that Elena and Jada, they both have the same line. So what does that tell you? That tells you that Jada and Elena, they have the same speed for the same distance. So that means if they are running, they are really like running side by side. Last question right here, who won the race? Since no one is faster and they both have the same speed, so the race will be a tie. Okay, so no one won, no one loses this race because it will be a tie with the same speed. Let's go ahead and write an equation now to represent both of them. So for Elena, the speed is 6 meters per second, so it will be y equals 6x. And then for Jada is going to be y equals, let's see, the speed will be 36 divided by 6, which is the same as number 6, y equals 6x. So we know that 6x equals 6x, so I'm going to combine these two equations together. 6x equals 6x. These right here, we learn about it. We call this infinitely many solutions. And if we graph an infinitely many solutions equations, this is how it's going to look like. The two lines overlapping each other. That's like the Jada's line and then Elena's line right there. So two lines overlapping each other, that means many solutions, infinitely many solutions. X could be anything and they're still going to be equal to each other.